Yes, John? Tak, John? Okay. No to już, to ja startuję. So we are starting, and retrosynthetic analysis. The idea comes from 50s and from Professor Corey from Harvard University. And basically what we are thinking about in retrosynthetic analysis is the focus on the product rather than on the reagent that will be taken for individual reactions. And let's suppose we have such a molecule which will be referred to as the target molecule, and we would like to make the disconnection as shown here. The disconnection, it means sharing electrons. So basically a bond means a pair of electrons, and we are sharing this. We can use similar system of the arrows for these disconnections as in traditional organic chemistry, third year organic chemistry, and we are using that kind of arrow for the indication of the retrosynthetic analysis direction. And what we will obtain is just following an arrow. We obtain a nucleophilic reagent here and the electrophilic reagent here. What we have here are nucleophiles and electrophiles, which mean we are a little bit far from the traditional reagent, from traditional molecules, which needs to be uncharged entirety. So further, what we need is to convert the syntons into the reagent. Basically, what I'm suggesting is to divide your paper or the table into two sides. On the left side, we'll note the retrosynthetic analysis. On the right side, all the conversion from syntons to reagent or synthetic approaches or any other notation that will be needed for our analysis. So what we have here is synton to reagent conversion, and to obtain such a reagent of the nucleophilic reactivity here, we need such an ending. It means hydrogen, because under the base, this could be transformed into the such kind of enolate with the nucleophile type of reactivity. So it is the first reagent, and then we'll take the second one, and to obtain the electrophilic type reactivity, we'll need something like, for example, halogen here. So a halogen, let's be chlorine or bromine here. Then, of course, we can note the synthesis, and the synthesis will be like this. Enolate plus such a Now we can use two tables, so it's a nice situation. And the product will be and finally we obtain target molecule and a chlorine ion. So that's the idea, and we can still be very precise with our notation, and to keep that kind of formality, let's now focus on something that we can call symptom chemistry. So basically, what we will define as synton. So a synton will be a set of certain atoms of certain groups which we are indicating in the target molecule, but in a such way that the syntons converted to the reagent will give us in a series of reactions which are known or which could be reliable a target molecule. So that's the definition, and of course we are performing the retrosynthetic analysis test as far as our reagent could be bought or could be synthesized in relatively easy laboratory procedure. So now a few words about the synton chemistry and how we are noting that, and what we see is that the key element here, the target molecules, are functional groups. So functional groups simply provides the selectivity. So define the selectivity within the carbon chain, and then say this atom and this atom are completely different carbon atoms. Their activity here are completely different. So what we could suppose is that we will obtain the nucleophile type reactivity here and the electrophile reactivity within this place. So coming to the synton chemistry, a formal notation will first of all should focus on a functional group, and let's say if we noted the heteroatom here, which is indicated by the F letter, so we can put the locus of 0 and following locus on the carbon atom of 1 to 5, for example, this molecule, and we could have two different synton types. So first is with the electrophile reactivity, and this type of reactivity, this type of syntons we will call acceptor syntons. Of the electrophile reactivity. So electrophiles, we can note it like electrophiles, yeah, and then we can have nucleophiles, and this will be donosyntons and nucleophiles. And then, of course, the donor with acceptor will give us the carbon-carbon bond. So what is the most important element of the organic synthesis? The formation of carbon-carbon bond. Okay, and now let's try to indicate the example of symptoms, So once more, I should also indicate the location of the nucleophilic or electrophilic reactivity within the synton, and for example, such a synton will be noted as acceptor 1, such a synton acceptor 2, and let's say such a synton will be donor 1, such a synton will be donor 0. Okay, let's now try to define or try to find the symptoms which we can observe, which we can find in organic chemistry. And so I'll prepare such a table in which I'll write here synton type, and here the reagent or the reacting equivalent, so reagents or reacting reagents. And of course, let's start from the acceptor symptoms. And first, what if we have such a symptom without any functional group? It shows how complicated is chemistry. Usually we have some group which remains, because this group should remain in the target molecule in order to be counted with our symptoms. So this type of symptoms will be called the alkyl symptom. So this is alkyl acceptor. And let's say the examples of the symptoms like that will be just R with halogen, and so this could be chlorine, bromine, iodine. However, also this could be tosylate or mesylate groups. So let's say something like that here, mesylate or tosylate, but also we can have the Friedel-Crafts reagent as we also have this kind of reactivity. So electrophiles, and now let's go to something with functional groups. And at first, let be symptom A1. A1 will be something like that. Functional group with a plus sign, and examples, so 0, 1, O, 1 here. And the examples are, of course, the carbonyl function, and the carbonyl functions could be available in such kind of the reagent, which have here the alkyl. So this is alkyl or hydrogen. However, also that kind of reagents a potential A1 reagent. So we can have, of course, chlorine, bromine, and while we'll observe the addition reaction here, we'll have the substitution in the second example. Of course, we can also have here the equivalent of the field product. With the acylium cation. So it was the second example, and then of course we go to A2. So A2 is something like functional group 0, 1, 2 with the electrophile type reactivity, and the examples of that, let's say, we'll have with halogen, so each one more is chlorine or bromine. Okay, here should be an X, not R. And then it is the first type of reactivity. The second type, let's say, will be something with the oxyran. So oxyran, let's say the reactivity of oxyrines will be nucleophile here, and we have O1, 2. So with the electrophilic center at the carbon atom of location 2. Then a double bond could be something that nicely provides such a reactivity. If we have here the electron withdrawing group, so a nitro function is electron withdrawing group, we have something like that, we will have the mesomeric structures having the electrophile here, so nucleophile will go to such a position, and it is a well-known Michaelis addition scheme. Okay, what if we go to A3 reactivity? So A3, once more. A3 is of course function here, O, 1, 2, 3, with the electrophilic location at the third carbon atom. And examples, of course, the most reasonable is that usually we can see that almost all the syntons we draw here as a functional group contain a carbonyl function. Why a carbonyl function? Because it's very useful. Usually also the available reagent, and the reactivity is very well defined. And if we draw something like that, we can see that at the third carbon atom and the first carbon atom does not have any connection. However, if we install here a double bond between these two carbon atoms, we obtain a conversation between these atoms. So let's say we could then have such a mesomeric structure with a plus sign, and a nucleophile will attack this position. So it is the first very important reactivity and very important reagent having the A3, so acceptor-free reactivity type. Then, of course, we could have something like that with, let's say, chlorine, bromine, I mean a halogen atom installed in that position. Of course, if we would like to have, let's say, a 4 reagent, we could also prefer something like that. However, let's concentrate on A5. So A5 A5, which of course with 1, 2, 3, 4, 5, a function here, and we see that it is simply, okay, it's not a case here, yeah, very sorry, here, A5, so we have something like that. A5, of course, and an example. So once more, why such an active position capable of a formation of the acceptors? And on one more, we have this free. So we have this free with a plus sign, and the nucleophile could attack this position. So we can see then once more we have installed here the conjugated two-double system, two-double bonding carbon atoms which are talking one with each other by the delocalization of the electron. So we discuss the nucleophilic, the electrophilic, so the acceptor type syntons, and now we are going to tono type reactivity. So let's start from D0, and the example of such syntons could be, let's say, we have the mercaptans or thiophenols, and so V0 basically is just a function with the nucleophilic reactivity of heteroatom, which is starting a numbering of the system, of a synton system, or just with some examples, especially with the aromatic ring here. Then let's say the second one, D1. An example of D1, this will be, of course, something like that, with the minus here. So 0, 1, an example. Is the nitro function, and potassium cyanide as an example of such a well-known reagent. Then D2, so a function and with the minus nucleophilic center at position 2. And the most often used reagent of such type will be ketones or equivalent of ketones or carboxylic acid and enolate type chemistry. So with the, let's say, a hydrogen atom here, so CH acid, and we can have the R group here, which could be hydrogen or alkyl, or we can have something like, once more, with the X here, so for carboxylic acid derivatives and such as esters or chloride, bromide, and so on. So of course, this type of enolates are formed and stabilized by the, so we are using a base to remove this hydrogen and obtain the enolates. These are stabilized by the mesomeric structures. So by mesomeric structures, and let's say we would have such kind of minus, which could be we could draw such a and basically then what we will have is the reaction with electrophile to form, in particular, carbon-carbon bonding. Then we could have, let's say, of course, the alkyl donor. So the alkyl donor will be just something like that. And these are, for example, organometallic compounds as lithium, so minus, plus, or Grignard reagent, so very well-known chemistry type. So these were the examples of the syntons, and now let's try to come back for the notation of synton disconnections. I should take a chalk here because my one is just finished. So basically what we could write here is we have here the O12, O12. So we have a donor 2 reactivity here, or O1 acceptor 1. So we can see that this was just clever enough to fulfill the chemistry of the syntons. It's a very natural way in which we proceed in that kind of chemistry. What if we change this? So what if we would like to make this connection in another way? So what if we disconnect our molecule in the same position, but using the opposite arrow direction? So let's note here it will be B, and here we can add A. We have once more here target molecule, and we would now have a plus sign here and a minus sign here. So basically O1, 2 will have the acceptor 2 and donor 1. We could observe that the chemistry we noted, we indicated for that this connection A is obvious even from our Ferdier cause, so it was relatively easy to find that in our Ferdier cause. And here the situation, I mean, when I would like to make this synton to reagent conversion, the situation is not so clear. Of course, we have the chemistry types that fulfill this type of disconnection. However, this demands further discussion. So I'm just leaving that for your own work, and let's try to find the potential conversion from this type of synton chemistry into a real reagent that could be used in our lab. So coming from that in silico or in brain analysis, retrosynthetic analysis, to a real lab, let's try to find the reagent and then to write the synthesis. So that's all for today, and thank you very much for your attention. Zatrzymujemy, bo to starczy na dzisiaj, bo i tak nie